Welcome back to Plate Tectonics Part 3. In this section, we will look at the evidence for plate tectonic theory, the mechanisms behind plate tectonics, and the formation of supercontinents. Some of the most convincing evidence for plate tectonics has come from drilling directly into ocean floor sediment. When we do this, we come up with a core that includes not only the oceanic crust, but a layer of sediment. And from this evidence, or from this drilling project, we see that the age of the deepest sediments, or the oldest sediments, are furthest from the spreading center. The thickness of ocean floor sediments verifies seafloor spreading. At the ridge crest, where divergence is occurring, sediments are almost completely absent. And as the plates move further apart, the sediment gets thicker and thicker and thicker as it moves away from the spreading center. In this illustration, you can see a model of seafloor spreading and the cores that are basically drilled and pulled up from the seafloor. So right at the mid-ocean ridge, where the seafloor is the youngest, you can see that there's almost no sediment. And as the plates diverge and move apart from one another, the thickness of the sediments increases with distance from the ridge crest. The photo below is the Chikyu, which is a state-of-the-art drilling ship that's used to drill up to 7,000 meters, which is more than 4 miles below the seafloor. A second line of evidence are hotspots and mantle plumes. So a mantle plume is a cylindrical upwelling of hot rock. The surface expression of a mantle plume is called a hotspot, which is an area of sustained volcanism. As a plate moves over a hotspot, a chain of volcanoes known as a hotspot track is built. The age of each volcano indicates how much time has passed since the volcano was over the mantle plume. Mantle plumes are stationary. They don't move, but the crust moves over them. One prime example that everyone knows about is the Hawaiian Island chain. So let's take a look at hotspots and hotspot tracks and what they tell us. In the top photograph, with the small inset illustration, you can see a rising mantle plume. And again, that mantle plume is hot magma that comes from near the core boundary, and it's stationary. It never moves its position. As it punches through the crust, it creates a volcanic island. As the plate moves over this plume, it creates this chain of islands called hotspot tracks. If you look at the Hawaiian Islands, you can see that Hawaii is about 700 million years old, and it's still being created. And then as you move to the northwest, Maui, which is just a little less than 1 million years old, Molokai, which is 1.3 to 1.8, Oahu, 2.2 to 3.3 million years old, and then Kauai, 3.8 to 5.6 million years. So what this tells us is that the mantle plume is currently under Hawaii, and the Pacific plate is moving to the northwest. So in the past, Kauai was where Hawaii is today. And then it moved off, and then Oahu formed, it moved away, and then Molokai formed, and so on. Now, in the image of the Earth, you can see where the Hawaiian chain is, and the Midway Island chain is part of this same chain, if you will, of volcanic islands. You'll also see the Emperor Seamount chain. It is actually part of the same mantle plume. So you can see that at some point in the past, the Pacific Plate, which today is moving generally to the northwest, was moving from south to north over this mantle plume. And in the bottom, you can see all the different hotspot and hotspot tracks around the Earth. For example, the Galapagos Islands, Easter Island, of course the Hawaiian Islands, the Marquesas, the Baja of California is actually a hotspot. The Azores off the coast of Spain are a hotspot track. A third line of evidence is paleomagnetism. So oceanic crust is made up of a type of rock called basalt. Basaltic rocks contain a mineral called magnetite, which is an iron-rich mineral affected by Earth's magnetic field. When the basalt erupts as magma or lava, it cools below what we call the Curie point. At this temperature, the magnetite grains align toward the position of the North Pole. So it's then, in essence, frozen in position and indicates the position of the North Pole at the time that the rock solidified. This is what we refer to as paleomagnetism. Paleomagnetism has two different lines of evidence. So the first is called apparent polar wandering. So through drilling projects and sampling projects, and then looking at the alignment of magnetite grains, we have discovered from rocks that range from 100 million years to 500 million years that on different continents, it looks like the North Pole was in a different place. Well, we know that that can't happen, at least not on that short of a time scale. So when we look at the idea that continents can move and we adjust these apparent polar wander paths, so you can see one in green for Eurasia and the one in red for North America. When we adjust for continental movement, you can see that these paths line up almost perfectly. So what this tells us is that the poles don't move, the continents move. So this apparent polar wandering also shows us that North America and Europe were joined together during the Mesozoic era, which is the age of dinosaurs. The other evidence that we get from paleomagnetism are magnetic reversals and more evidence for seafloor spreading. So during a magnetic reversal, Earth's magnetic field will periodically reverse polarity, where the North Pole becomes the South Pole and vice versa. So rocks that exhibit the same magnetism as the present day magnetic field exhibit, we call that normal polarity. Rocks that exhibit the opposite magnetism, meaning that their magnetite grains align in a different direction, exhibit what we call reverse polarity. There is a thing called the magnetic timescale, and it shows the sequence of shifts in the polarity of Earth's magnetic field, which is determined from lava flows. So our ocean floor, which is basically made up of lava flows at divergent plate boundaries, is a magnetic recorder. You can see in the illustration to the left, it's a stylized, ideal representation of what these reversals look like. So in the middle, you can see the ridge axis, and the white color represents normal polarity. That's what we have today. As you move away from the ridge with divergence, you'll get a series of orange stripes, white stripes, orange stripes, and you can see that on either side of the ridge that they're roughly the same size. So you can see a series of reverse polarity, normal polarity, reverse polarity, and so on. And that is a magnetometer record, which basically we tow a magnetometer behind a ship and we record the alignment of the magnetite grains across a mid-ocean ridge. And what we get is what's on the right. So you can see the green line is the axis of the Juan de Fuca Ridge off of the northwest coast of the United States. And you can see at the ridge, we've got normal polarity, and as it moves away, we have a series of reverse and normal polarity on each side. For me, one of the most convincing evidences for plate tectonics are the earthquake patterns. So earthquakes are associated with plate boundaries. Deep focus earthquakes occur along trenches, so these submarine or deep ocean trenches, and they provide us with a method for tracking a oceanic plate's descent into the asthenosphere. In this map, you'll see the blue, the yellow, and the red dots. These all represent distributions of earthquakes at plate boundaries. And here we're looking at the Pacific Plate. So if we look at the west coast of South America, for example, right at the edge of the continent, you see a lot of blue dots. These are shallow earthquakes. Then you'll see a series of yellow dots. These are intermediate. And then a thin line of red dots. These are deep focus earthquakes. So what is happening is the plate, the Nazca plate, which is an oceanic plate, is subducting beneath South America. And as the plate goes deeper below the South American continent, the earthquakes get deeper. So what those red dots show us is how far the Nazca plate has subducted beneath the South American continent. So it's essentially the leading edge of the Nazca plate. So this area where these deep focus quakes occur is called the Wadati-Benioff zone. And in the illustration on the right, you can see that at the trench, you've got the blue shallow quakes, and then you've got your intermediate quakes here in green, and then your deep focus quakes showing the leading edge of that subducting plate. And again, on the left, you can see Japan as an example. So you've got the Japan trench with blue shallow quakes, then intermediate quakes, and then deep focus quakes. And what this is showing is where the Pacific plate, how far it has subducted beneath Japan. So how do we measure plate motion? There is geologic evidence by knowing the age of the seafloor and the distance from the spreading center. We can calculate an average rate of plate motion. So that's a very simple geologic way to get an approximation of plate motion. We can also, with today's technology, measure plate motion from space. And this is accomplished by using GPS, the Global Positioning System, to measure various points on Earth's surface. GPS data are collected over various points repeatedly for many years to establish plate motion. And since GPS is relatively new, it took decades of collecting data before we were actually able to use it to measure plate motion from space. So this map shows us plate motions. The red arrows show the approximate movement of the various plates. So for example, the African plate is moving generally to the northeast. The Nazca plate is moving eastward. The Pacific plate, as you can see, is moving roughly to the northwest, whereas the American plate is moving to the west and slightly to the southwest, overriding the Pacific plate. So what drives these plate motions? Researchers agree that the primary factor that drives plate motion is convective flow in the mantle. And that was first proposed in 1927. So it is the basic driving force of plate tectonics. Think about water boiling. When it starts to get to a rolling boil, you can see it swirling around from the bottom of the pan to the top and then back down. This is what convective flow in the mantle is like, though on a much slower scale. Now, there are forces that assist plate motion. And remember earlier when I talked about the rate at which plates move apart or diverge. In the mid-Atlantic, it's about 2 centimeters per year. But in the East Pacific rise, it's 15 centimeters per year. So why the difference? Well, it's these forces that assist convective flow. So the subduction of cold oceanic lithosphere is a force called slab pull. So as that slab is pulling down or pushing down into the asthenosphere, as it gets deeper, it starts pulling the rest of the slab behind it at a faster rate. And then we have the force of gravity acting on the mid-ocean ridge, which is elevated, and it is basically a force called ridge push. So in the area of the East Pacific rise, we have ridge push and slab pull in addition to the convective flow of the mantle. So this is why we get a 15 centimeter per year movement versus other areas like the Mid-Atlantic ridge at 2 centimeters per year. So here's a good illustration of slab pull and ridge push. You've got a trench with the subducting slab, and as that slab pulls further down, the mantle drag kind of resists plate subduction, but the slab pull from that sinking of a cold dense slab basically overrides the drag a little bit and starts pulling it along faster. In the meantime, ridge push, which is driven by gravity, is basically pushing that slab even faster. All the while, convection, represented by the two yellow arrows moving away from one another, enhances that motion when the velocity of the asthenosphere exceeds that of the plate above it. So we've got a couple of different models. Actually, we have several different models of how convective flow works in the mantle. On the top, in A, we've got the whole mantle model. And what the whole mantle model states, or basically relates to us, is that we have hot rising plumes, mantle plumes from near the core boundary that are stationary. So this is where heat is moving up and out of the center of the earth. As the mantle plume gets toward the surface, it cools off, and then the cooler upper mantle sinks back down. So you get this motion, this convective motion, which is also aided by subducting slabs, which are cold and descending into the mantle. So the mantle plume is the hot upward motion toward the outside, and the subducting plate is the cold downward or descending portion of this convection cell. In B, you've got the layer cake model. And the layer cake model says that we have two basically disconnected convective layers. So we've got a really dynamic upper layer that's driven by descending slabs of cold oceanic crust, and a more sluggish lower layer that carries heat upward without really mixing with the layer above. I do not agree, to be honest, with the layer cake model. The layer cake model does not allow for two things. It does not allow for the mantle plumes from the core boundary that we know exist. It also does not allow for there's a thing in the earth near the core called the D layer. The D layer is a layer of really cold broken bits of oceanic crust that have made it really deep. And we know this from tomographic studies of the interior of the earth. So we know that subducting oceanic lithosphere goes really deep, and we know that magma plumes rise from near the core boundary. So in my opinion, the whole mantle model is more correct than the layer cake model. So the next question we ask is, how does plate motion affect plate boundaries? So the total surface of Earth does not change, despite movement along plate boundaries. So plates can grow or shrink depending on the type of plate boundary that surrounds each plate. For example, the African plate is surrounded by divergent boundaries, and it is growing over time as new crust is built along these boundaries. But the Pacific plate, which is surrounded primarily by convergent boundaries where crust is being destroyed, is shrinking over time. And the rate of divergence and convergence on Earth are roughly equal to one another. So one of the questions we ask ourselves when we study Earth history is, when did tectonics start? Plate tectonics did not begin immediately after Earth's formation, and our most current data suggests that it began approximately 3.2 billion years ago. That's about 1.4 billion years after Earth's formation. The Earth is 4.6 billion years old. So how do we know this? Two studies that are ongoing. One done in a portion of the Pilbara Craton in Western Australia, which is one of the oldest pieces of Earth's crust. Scientists basically found a latitudinal drift of about 2.5 centimeters a year and dated that motion to 3.2 billion years ago. Concurrently, there is a scientist, a geochemist, studying inclusions in diamonds. And he's analyzed those inclusions and found that the inclusions are minerals that are formed at Earth's surface. So how did they get in the diamonds? Because we know that diamonds form deep in the earth. The only way that minerals from the surface could be included in diamonds that form deep in Earth's mantle are through plate tectonics, through subducting slabs, bringing those minerals down into the deep mantle. Now, these minerals have not been found in diamonds older than 3.2 billion years. And I've included a link to a short video that's an optional video about this scientist and his work with these diamonds and how he basically analyzes these particular minerals. So what about supercontinents? Supercontinents like Pangaea form cyclically. They are a product of two different cycles, the supercontinent cycle and the Wilson cycle. The supercontinent cycle is a periodic aggregation and then dispersal of Earth's continental crust. The most recent supercontinent is Pangaea, and it formed about 300 million years ago during the Paleozoic era, basically at the end of the Paleozoic during the Permian period. One view of the supercontinent cycle proposes a whole series of supercontinents. Valbara, Ur, Kenorland, Columbia, Rodinia, and then Pangaea. And you can see that in this illustration to the right, roughly what it's estimated that these different supercontinent configurations were. After Pangaea, there was Pangaea. The Wilson cycle is a model that goes hand in hand with the supercontinent cycle, and it describes the opening and closing of ocean basins and then the subduction and divergence of tectonic plates during the assembly and disassembly of the supercontinents. The cycle basically has 6 stages, and it begins because thick continental crust does not conduct heat as readily as thinner oceanic crust. So in this illustration on the right, you can see the 6 different stages, from embryonic, which is stage A, all the way through suturing, which is stage F. So this illustration is great because it tells us what motion is involved with each stage, and then it gives us what happens physically to the Earth, and then a good example. So today in the East African Rift Valley, that's embryonic stage A, which the motion is uplift, and it basically creates a complex system of these linear rift valleys on a continent. And then the juvenile stage B is divergence, or seafloor spreading. And that's where you get a narrow sea with a matching coast, like the Red Sea. The mature stage, we still have divergence and seafloor spreading. And that's where we get a ocean basin with continental margins. So a good example is the Atlantic Ocean. Then the declining stage is where convergence and subduction start. So the Pacific Ocean is in the declining stage. The terminal stage is where we've got convergence, but we also have collision and uplift. So the Mediterranean Sea is in the terminal stage. And then suturing is where we have convergence and uplift, or mountain building. And these are where we have young to mature mountain belts. So the Himalaya are in the suturing or final stage of the Wilson cycle. So when will we have the next supercontinent? If you could fast forward about 250 million years in the future, Pangaea Ultima is projected as the next supercontinent. Now, other names have been proposed or given to this supercontinent, including Pangaea Proxima, Neopangaea, Pangaea II. But basically, if you look at the illustration on the right, this is what Pangaea Ultima will look like, and this is based upon current tectonic movements and the rate of movement, and fast forwarding it 250 million years. This is the end of the plate tectonics background lecture. In our next lecture, we will look at sedimentary rocks, which are basically the containers of fossils.